We are working our way through the different model terms that are possible in a regression model. We've looked at the interaction terms. In this one, I want to take a look at the quadratic terms. I think this will be a little bit easier than maybe the interactions. We'll see. Let's start with our model. Our interaction model is the model that allows for a curvilinear relationship between y and x. And you notice I only have a single x here. I don't have an x1 and an x2. In a later video, or later videos, I guess, we will put these model terms together. We'll put interactions with quadratics with the qualitative variables. Here I'm just going to look at a single x and what this allows for, what the squared term, and that's what I want you to think of when let's do a different color here because I use red. When you see the squared term, that's a quadratic term. Now if you see x1 squared times x2, which we will later on, it's a quadratic term. It's also an interaction term, right? Because when you multiply two x's together, you get an interaction term. What this allows is one of these two relationships. If you're here on the right, we talk about this being positive curvilinear relationship, or a upward curve or upward curvature, positive curvature, just some different terms that are used. And over here on the right, you have the negative, the downward curvature. You got a smiley face and a frowny face. How's that? Pretty good, huh? Right? All right, so you get the rate of increase or decrease in y changes as the value of x gets larger. And if you think about this rate of increase, you can think of that as a slope. And some of you might remember, and it's going to be tough for me to draw with the mouse, some of you might remember if you want to find the slope of a curve, you draw what's called the tangent line. That's not too bad. There's supposed to be a straight line. If there's a curve, a straight line will only touch the point in one spot, or touch the curve in one point. That's called the tangent. And that's what the slope of the line would be. And you can see as you curve on down here, the slope, oops, that's a terrible one, but the slope changes. And so you could think of a curve as a line with an ever-changing slope. Let that one linger for a second. A curve is a line with an ever-changing slope, or you could just call it a curve. That works too. And so we have this curvilinear relationship. If I have some data points, and I think we actually saw a pretty good example of this. Remember the diamond data? The diamond data look like this. This caret size versus the price. It looked more like that. It's not a bad illustration of it either. We can fit a straight line to the data, but we do better. I don't know how this color is going to play. Nice yellow there. We do better with a curve. And so we want to allow for that curvilinear relationship, and so we're going to add the squared terms to our model. Now it's only going to make sense to square the quantitative terms. So x is I'm assuming x is a quantitative term here. Now we're trying to predict the price of a house based on the size. We're trying to predict the price of a diamond based on the size of the diamond. So quantitative variables you can square, and it allows for curvilinear relationships. Of course, one of the things we're going to want to know is, do we need those curves? And we'll get to that. So we'll talk about testing in a second. Before we do that, let's talk about some beta interpretations. You didn't really hear me talk about beta interpretations with the interaction model, did you? And that's because the interaction really is taking a look at different slopes. So if you're taking a look at different, or let's call them non-parallel lines, if you're taking a look at non-parallel lines, there's a slope and y-intercept interpretation for each line. But it gets more challenging when interaction is present because there's a bunch of them. Here with the quadratics, we get different interpretations. We don't have a slope any longer. And so the beta interpretations, beta naught still represents the y-intercept. Okay, same interpretation that we've seen before, except now we're working with a curve. Still has a y-intercept, but it's a curve. Same questions. Does the value of x equals 0 make sense? Did we sample over the range that included x equals 0? So that's why I say it may be practical, it may not be. Same questions we have to ask whenever we talk about the y-intercept of a curve. The beta 1, you want to say it's a slope, but it's not, because remember, we don't have a line, we have a curve. Beta 1 moves the curve along the axis. It's referred to as a shift parameter. We don't really get any kind of practical interpretation from beta 1 when we're working with a curve. The only, most of the time, beta naught's not practical either. The only one that we really take a look at is the rate of curvature. Is it positive or negative? Depending on the data set you're working with, you may have a pretty good feel for the data, you may not. There's a data set, the size of the house versus the cooling cost. It's not a straight line. That data tends to look like this. As buildings, homes, factories, whatever you're working with, as they get bigger, the cooling cost starts to slow down. It's not a straight line relationship, it's a curvilinear. It costs more to cool the first square foot than the 1,000 square foot, than the 10,000 square foot, than the 100,000th square foot if you're talking about a big factory. And so the cooling costs change. The relationship between size and cooling cost changes as the building gets large. Okay, it varies. And so the y-x relationship is more of a curve. It's a downward. I would expect beta 2 in this case. I would expect beta 2 to be less than 0. Sometimes you know, sometimes you don't. I'm not really expecting you guys to know the direction of your quadratic curve in your projects. I'm not really expecting that. Just some beta interpretations. Again, our focus, we don't want to focus on the beta interpretations, but they are some things that you can learn. You can get some extra information. We're interested in predicting y as accurately as possible. A curve may be better than a line. But it's worth noting here, beta interpretations are going to be very specific to the model. If you have a straight line, you got a slope and a y-intercept. Here we have a slope, a shift parameter, and a rate of curvature. And so you got to really be careful. Take a look at the model that you're working with and then try to figure out how we interpret the betas. And I got one more beta interpretation for you when you're working with qualitative variables, but I'll do that in another video. All right, so what's our approach to quadratics? Hopefully, this will make sense to you. Hopefully, this will seem like what we did with the interaction. So I've added the model again. I don't think you have this in your notes, but I wanted to have it on this slide as I talk our way through it. You have it on previous slides. If this is the model you want to consider, this is the model. It's a single curve. You know, maybe we're saying it looks something like that if we're talking about the cooling cost example. Here's y. Here's x. All right, so how do you think we're going to begin? Not a trick question. How do we always begin our model building? We're going to do a global f-test. Now, let's see where you're at. Test yourself here. What do you think the null hypothesis is going to be here? If you're testing everything in the model, which are the betas that are attached to the x's? Well, in this case, we just have two of them, right? Beta 1 is attached to the x term. Beta 2 is attached to the x squared. And really what we're asking here, do any of those terms work? What's the null say? The null always says no. They don't. So it's going to say beta 1 and beta 2 are equal to 0. In other words, this part of the model doesn't work. The x, the linear, the curvilinear, nothing works. The x's are not useful for predicting y. Now, hopefully, we're going to reject that and say, yeah, something works. Go for the most complicated. What's the next test? We're going to go for the most complicated term in there. Well, the most complicated term in this model is the quadratic. And again, in your notes here, and it's funny because I put this in your notes now, and it may not mean a whole lot to you now. It will later as you look back. You have to take a look at how many quadratic terms are there. And of course, I'm giving it to you in this video in the simplest form possible. A single quadratic term, that's an individual. That's going to be what we call a t-test. What's the beta attached to the quadratic? Beta 2. So null's going to say, yeah, well, the quadratics don't work. All these subsequent tests, as we work our way down, we're assuming that we reject H naught here. We got to reject. We got to say something works, because if we say fail to reject, there's insufficient evidence to indicate anything is useful, we would actually stop. Something I will not let you do on your fourth project, or your I guess your multiple regression project. Let's say it that way. So we're assuming something works. Now we're looking for it. Is the quadratics? We're going to go ahead and test for it. And then you work your way down. We may have additional tests if applicable, and we'll get more into that with the model building. Again, I'll say this. If the quadratic terms, you heard me say this with the interaction, right? If the quadratic term is useful, if you say, yeah, I need a curve, we don't test x. So if x squared's in the model, we don't test x. Just like I said, if x1, x2 is in the model, we don't test x1, we don't test x2. And think about it. If the quadratic is necessary, we would have rejected this test right here. We would say beta 2 is not equal to 0. Sufficient evidence to indicate the quadratic is useful. We need the quadratic. Now, if I said test to see if x is useful, to test to see if x is useful, you would test both beta 1 and beta 2. It's an unnecessary test because we already know the quadratic is needed. And so generally we just say it this way, and it applies both to interaction ideas and applies to the quadratic ideas as well. And you'll see this play out in a video I talk about later on called the game plan, which is a model building video. I like showing it to you ahead of time, and I know by doing that, sometimes I have discussions with you as we're building the material, and I'm talking about this stuff, and you might be thinking, what? Where's that coming from? And sometimes what I'm doing is I'm just planting seeds. I'm just throwing ideas out there, and if you see it in its smallest form here, maybe you say, all right, that makes sense. If I didn't throw these seeds out there, if I didn't do this groundwork, all of a sudden I get to that model building, that game plan video, and you guys blow up. It's like, holy cow, there's a lot here. And what I'm going to try to point out to you is there's not a lot in that video. I mean, it seems like a lot, and I'll grant you that. But if you look at it for what it really is, it's sort of the same idea repeating itself over and over and over again. And really, over and over and over again. It's going to be a bunch of times. If you get the idea, it's a pretty straightforward video and idea. If you don't get that little idea, it's just repeated over and over and over again. It's just like, yeah, I still don't get it. You will. You will. And a lot of those ideas I'm telling you bits and pieces of, and this is one of them. So if this idea doesn't make a whole lot of sense right now, don't worry about it too much. We'll come back, we'll revisit it, and you'll see it again. The main idea with our testing models, we start with everything to see if anything works, and then we kind of work our way down and start focusing on little pieces here and there. Whether we call it, if we test everything, that's called a global. If we test an individual term, that's called an individual or a t-test. If there's 2 or more, but not all, and so our models are going to get bigger. Say our model has 10 terms in it, and we want to test 4 of them at one time. That's part of the model. That's called a partial test. And again, I'll talk more about the tests in a specific video that you'll see in a little bit. But that's how we would approach the quadratics, and that's a good place to stop. So we got the interactions out of the way, we got the quadratics. Last term, next step is to do the qualitative variable. So we'll look at that in another video. So long.